Ablation is interaction blind and local. FANOVA is global but conflates sensitivity with value. HyperSHAP is a unifying framework that addresses both deficits using cooperative game theory, Shapley values and their interaction generalizations with axiomatic guarantees. Let's state the gaps precisely. Ablation explains the incumbent relative to the default but ignores interactions and is order dependent through its greedy path. FANOVA measures variance contribution, so sensitivity, which is not the same as the benefit of tuning. A hyperparameter can be highly sensitive, yet offer no headroom over the baseline. 3 questions remain unanswered. Which hyperparameters are worth tuning, as opposed to merely being sensitive? Where does a specific optimizer fail to exploit the structure of the search space? And how do we quantify interactions without order dependence? HyperSHAP answers all 3 via a family of 4 explanation games built on Shapley values and Shapley interaction indices. Shapley values attribute individual contributions. To capture synergy and redundancy, we use the Shapley interaction index. For a pair, it replaces the marginal contribution with a discrete second-order difference. Nu of S union ij minus nu of S union I minus nu of S union j plus the nu of S. The standard inclusion-exclusion term, again averaged over collisions with appropriate weights. The sign is interpretable. A positive interaction indicates synergy. The pair is complementary, jointly worth more than the sum of the individual effects. A negative interaction indicates redundancy. The hyperparameters are substitutes. 0 indicates separability. Because the index is defined over coalition symmetrically, it is free of the ordering artifacts that plug greedy ablation. The framework itself is a set of games, all instantiating the players as hyperparameters but differing in the characteristic function U. And it is the choice of characteristic function that fixes the question being asked. The diagram organizes the 4 games: ablation, sensitivity, tunability, and optimizer behavior. The design point is modularity. One game explains a specific incumbent configuration, another quantifies tunability, others probe optimizer behavior, and each inherits the Shapley axioms and the interaction index. Any game also lifts to a distribution over datasets by aggregating game values, for example the mean over benchmark suite, which supports general dataset agnostic conclusions rather than instance-specific ones. Here, we will limit ourselves to ablation and tunability though. The first instantiation of HyperSHAP recasts ablation game theoretically. Given a target, the HPO result, and the base, the default, defined for any coalition as the hybrid configuration that takes target values on S and base values on the complement. The characteristic function is the performance of that hybrid, similar as in ablation, in the ablation path analysis, written here as 1 minus the cost. Applying the Shapley value, each hyperparameter's attribution is its contribution to closing the performance gap between the default and the incumbent. And the interaction index quantifies pairwise interactions for this specific configuration pair. The advantage of a greedy ablation is decisive. No path dependence and interactions are captured exactly rather than absorbed into whichever coordinate is flipped last. The second game, tunability, formalizes the benefit of tuning rather than sensitivity following probes et al. The characteristic function of a coalition S is the best achievable performance when the hyperparameters in S are optimized and the remainder are held at the baseline value, a maximization inside the value function. The contrast with sensitivity is sharp. Sensitivity measures variance in any direction. Tunability measures the maximal possible gain. Tunability is monotone in the coalition, enlarging S cannot decrease the best achievable value, whereas sensitivity is not. Sensitivity is confounded by domain size. Tunability is not. And the diagnostic case, when the baseline already equals the optimum, tunability correctly returns a 0 importance for this parameter, while a variance-based score remains positive. The monotonicity and the correct 0 are exactly the properties one wants from a should I tune this measure. Computationally speaking, tunability appears prohibitive. evaluating the characteristic function for each coalition naively requires a separate constraint HPO len. The practical resolution is again surrogate-based, approximate the inner maximization over configurations with the surrogate rather than re-optimizing. An important empirical finding, well, ablation and tunability can diverge, and the divergence is diagnostic. Ablation reveals which hyperparameters the optimizer actually exploited. Tunability reveals which hyperparameters could yield gains. A hyperparameter that is highly tunable but untouched by the optimizer signals unexploited headroom. A statement about the optimizer, not just the search space. Here we are seeing two games side by side on a real instance. Ablation on the left, tunability on the right. Each showing first order attributions together with the interaction structure, red for synergies and blue for redundancies. And we can see two types of plots. An upside plot showing effects in terms of a bar chart and a Shapley interaction graph visualizing main effects directly at the nodes and interactions in the form of hyperedges. What we can see here is that tunability identifies two hyperparameters to be very important individually, but with a negative interaction, meaning tuning both of them is redundant and not necessary. On the left hand, we can see the results of ablation for a tuned hyperparameter configuration. What we can see here in particular is that the optimizer chose to tune Li, the hyperparameter, Li, since tuning both hyperparameters, Li and Om, is not necessary, it is redundant. The point here is not the specific values, but the form of the output, a single axiomatically grounded representation that simultaneously reports per hyperparameter contributions and their interactions for whichever question the characteristic function encodes. To sum up, ablation as a game explains hyperparameter values. Tunability quantifies the effect of tuning individually or in sets. Tunability is provably distinct from sensitivity. It directly measures the benefit of tuning and is monotone, whereas Fanover measures variance. Interactions are first class throughout. The Shapley interaction index captures synergies and redundancies without order dependence. The unifying statement, HyperSHAP attributes performance contributions with principled interaction-aware Shapley guarantees, subsuming the partial answers that ablation and Fanover provide.